Okay, so we have the derivatives of logs and exponential functions today. So we first start off with the derivative of a logarithmic function. So if you're given the common log function where f of x equals log base a of x, then the derivative for log base a of x is going to be 1 over x times the natural log of a. So there is the common log derivative. The chain rule common log derivative. So if you have log base a of some function g of x, then the chain rule derivative is going to be the derivative of the inside function over the inside function times the natural log of a. So g prime of x over g of x times the natural log of a. So we could write this as g prime of x over g of x times the natural log of a. Okay. And then the derivative of the natural log is just 1 over x. That one's nicer. So derivative of the natural log is 1 over x, and the derivative chain rule derivative of the natural log of g of x is going to be derivative of inside over the inside. So g prime of x over g of x. Those are the derivative formulas for common logs and natural logs. So let's go ahead and try them out below. Okay, so number one, we have f of x equals log base 10 of 2 plus the sine of x. This is going to use the chain rule derivative for the common log function. So what is the derivative of the inside? What's the derivative of 2 plus sine x?
Negative cosine x.
Just cosine x. And you put it over the original inside times the natural log of the base. So what am I writing?
2 plus sine x.
2 plus sine x times what?
ln.
The log of 10, or just log, sorry.
Natural log of 10. There you go. That's it. All right. 2. F of x equals the natural log of x cubed plus 1. This will use the chain rule derivative for the natural log. So this one's even easier. It's just the derivative of the inside over the inside. So what is the derivative of the inside?
3x squared.
3x squared. And we put it over the original inside of
X cubed plus 1.
That's it. All right. Perfect. Okay, any questions so far? Just follow those formulas and you'll be all right. Okay. 3, the derivative of the natural log of the sine of x. Again, this is going to use the chain rule derivative for the natural log. So what is the derivative of the inside function?
Cosine.
Cosine over the original inside, which is
Sine.
sine. All right, you get cosine over sine, but what identity is that?
Cotangent.
Tangent.
Cotangent.
Ah.
There you go. So the derivative of the natural log of sine x is cotangent x. Weird, right? Okay. Now we have the square root of the natural log of x. So we know we can't take the derivative in this form, so we must rewrite this as the natural log of x to the 1/2, where we use chain rule for the outside. So we're going to say f prime of x And what number's coming down?
1/2.
1/2 times the natural log of x to the what power?
-1/2.
-1/2 times the derivative of the inside function. What's the derivative of the natural log of x?
1/x.
1/x. I may have muted you, Ryan. There's some weird car noise going on. I don't know if it was you or somebody else. Unmute yourself if you want.
No, I had my mic muted, just not on Zoom, so it wasn't me.
Yeah. Yeah. All right. So there it is. There's the derivative of outside times derivative of inside. So let's make it look pretty. So I'll put these two together first. So that'll be 1/2x times the natural log of x to the -1/2, which then can be rewritten if you flip the negative exponent to the denominator. You'll get 1/2x times the square root of the natural log of x. Yeehaw. All good? Woohoo, thumbs up. Sweet. All right. All right. Next, the derivative of the natural log of x plus 1 over the square root of x minus 2. Oof. Oh boy. Well, what would you have to do to the inside function?
Rationalize.
Well, you could rationalize, but that'd be more work. So all we want to do is take the derivative. So this would use a chain rule derivative of the inside. And when you take the derivative of the inside, what rule would you be using?
The quotient rule.
Exactly. It'd be the quotient rule, which means this is going to be a nightmare, right? But here's where logs come to save your life. If I wrote the natural log of x over y, how could I expand that?
Natural log of x and natural log of y.
Natural log of x minus
Minus.
natural log of y. So what's stopping us from using that rule on the expression above? Nothing at all. Which means that our derivative just got easier. Which means that we're not done simplifying yet. We can't take the derivative yet because we have to rewrite this radical. Which means that you get d over dx of the natural log of x plus 1 minus the natural log of x minus 2 to the 1/2. But now we're almost done. We can't take the derivative yet because what could you do with that 1/2? I'm asking you to dig deep into your natural log formulas. What if I had the natural log of x to the n? No derivative, no calculus involved, just algebra. What could I do with that exponent of n?
Bring it to the front.
N times the natural log of x. The power rule for logs. So now I get the natural log of x plus 1 minus 1/2 times the natural log of x minus 2. Have we done any calculus yet? No, we haven't done any calculus. But now we're ready for the calculus because we can now do the chain rule derivatives for these natural logs. So now we are ready for the derivative. So looking at the natural log of x plus 1, remember the chain rule derivative for the natural log is derivative of inside over the inside. So what is the derivative of the natural log of x plus 1 going to be?
1
Over,
x plus 1.
there you go, minus 1/2 times the chain rule derivative for x minus 2, natural log of x minus 2. What's that derivative going to be?
1 divided by x minus 2.
There you go. Now the calculus is done. And we just clean it up by saying 1 over x plus 1 minus 1 over 2 times x minus 2, and that's done. So you see how logs can make your life easier. Unless you really wanted a quotient rule that inside, did you?
So why didn't we do that on number 4? Is it because it's already given like that?
Because it's not the natural log of something to the 1/2. It's natural log x all raised to the 1/2.
The whole thing rather than just.
So no, that's a good question, because remember for this one, if it was natural log x to the 1/2, then we can move it down.
It's because it's to the x, it's tied to the x only, right?
But since it's natural log of x all to the 1/2, these are two different things. They are not the same.
For sure.
So no, that was a good question. Or maybe I'll leave that there, right? I'll say natural log x to the 1/2 is not the same as natural log x to the 1/2. Okay. All right. So since we see that logs make derivatives easier, we come across something called logarithmic differentiation. So if we come across a complicated derivative, what we'll do is apply the natural log to both sides, because the natural log is easier to work with than the common log. So we'll apply the natural log to both sides, and then we'll simplify the more complicated side. And once everything's simplified, we'll take the derivative on both sides and solve for y prime. Okay. Because if you look at number 6, if you did not know about logarithmic differentiation, what derivative rules would you be applying to this problem?
Everything.
Everything. It'd be a quotient, and then the numerator would be a product, and it would be a product with a chain rule, which is just going to be very miserable, also because of that power of 3/4. So here's where logs make your life easier. But I guess before we begin, let's write our 3 main log rules, the easiest log rules. So first would be product to sum, log xy, I'll do natural log. Natural log xy gives me natural log x plus natural log y. Natural log x over y gives me natural log x minus natural log y. And then natural log x to the n gives me n times the natural log of x. Do not mistake the logarithmic power rule for the derivative power rule. When you do a derivative power rule, you take one away. Are we doing that on this property?
No.
No. So do not make that mistake. Students like to say, oh, I brought the power down. I did the derivative. Do not make that mistake. These are the 3 log rules, log properties that will save your life. Okay. And you learned them all the way back in 1414. All right, so let's go ahead and get started. How much can I zoom in? There we go. So we want to take the derivative of this equation, but we say, hey, that looks really complicated. So what we're going to do is apply the natural log to both sides. We'll say natural log y equal to natural log of all of this. X to the 3/4 times the square root of x squared plus 1 over 3x plus 2 to the 5th. Which means now we will worry about the right side. The right side is the more complicated side, so that's the one we are going to simplify by our log properties. Okay. I think my laptop froze. Move, move, move. Well, it froze on the screen, but it's working in front of me. All right. Let's see if it catches up. Or maybe not. Still says I'm on Zoom. We're good there. We're good there. Okay. Come on, laptop. Oh, no. Okay. One moment. It just broke. Okay. But since I wrote that down already, go ahead and try to expand the right side by the log properties I wrote above. And when I get this working again, let's see. There we go. We're back. Okay. These computers won't handle being remote for much longer. Okay. So here we have the natural log. And now to expand this, I'm first going to use the quotient to difference. So this is going to become the natural log of x to the 3/4 times, and I'm already going to rewrite the radical as x squared plus 1 to the 1/2 minus the natural log of 3x plus 2 to the 5th. So we just did quotient to difference. And now we're going to have to break up this natural log by doing product to sum. So this means that you'll get natural log x to the 3/4 plus natural log x squared plus 1 to the 1/2 minus natural log 3x plus 2 to the 5th. All right, everybody good so far? Okay. And now, after we did quotient to difference, product to sum, we are now going to do the logarithmic power rule. So we get 3/4 natural log x plus 1/2 natural log x squared plus 1 minus 5 times natural log 3x plus 2. And have we taken the derivative yet?
No.
No. Now we take the derivative. We have simplified everything by the 3 logarithmic rules above. So now we take the derivative with respect to x on both sides. So I'll just say d over dx everything. Okay. So the left side, since you're taking the derivative of x, the derivative of the natural log of y with respect to x, this is going to be an implicit on the left side. So when we take the derivative of the natural log of y with respect to x, you're going to get the derivative of the inside, which is y prime, over the inside, which is y. And now we handle the derivative on the right side. So 3/4 times the natural log of x. That 3/4 will stay there. And what's the derivative of the natural log of x?
1 over x.
1 over x. Plus that 1/2 will stay there. But now we have a chain rule derivative for natural log of x squared plus 1. What is that derivative going to be?
Two x over x squared plus 1.
There you go. Minus 5 times, and again, one more chain rule. What's the chain rule derivative for natural log of 3x plus 2?
3 over 3x plus 2.
That's it. And now we have y prime over y. Let's clean up. I get 3 over 4x plus here, my 2's will cancel. So I'll get x over x squared plus 1 minus 15 over 3x plus 2. So everything's nice and cleaned up on the right side. And now we have to solve for y prime. So all I'm going to do is take this y and multiply it to the right. And y prime is going to equal y times all of this. 3 over 4x plus x over x squared plus 1 minus 15 over 3x plus 2. And now we do a quick substitution because what was y originally?
X to the 3/4 times the square root of x squared plus 1 over that number right there.
All of that, right? That's what y is. So you plug that in for y. So you get y prime equals x to the 3/4 times the square root of x squared plus 1 over 3x plus 2 to the 5th times, you can do brackets or parentheses. I like brackets because it just looks neater. 3 over 4x plus x over x squared plus 1 minus 15 over 3x plus 2. There it is. And if you attempted product rule, quotient rule, chain rule on this, you would still be gone. So word of caution, on the next exam, there's 2 problems that say use logarithmic differentiation. Stated boldly. If you go ahead and try to attempt product rule or chain rule and quotient rule, you get no points because it says use logarithmic. Read the directions.
Wouldn't you be proud though?
No, because you'll never get the answer. Nobody has.
Take forever.
Mhm. You'll spend your whole day just trying to get the answer. And I'll still count it wrong because you didn't use logarithmic. All right. Any questions on this one before moving on? All right, then. That means that go ahead and try number 7 out on your own. So use the logs, simplify it, and then take the derivative. You want to do this one, Ryan?
Wait, what? Nope.
No? All right, cool.
That's what you get for muting me, bro.
Hey, man. People get mute. Sometimes it be like that, okay?
Rude.
Sometimes it's like Cole going to St. Patty's Day and catching COVID.
Oh, he 100% got COVID.
It was crazy.
COVID Cole. That's his new nickname.
Ooh. All right. Oh, no.
What'd you do?
I was looking at the stock market.
Ah, that's unfortunate.
I was like up 100 points. That means I made money. But then I looked and nope, I lost money. Dun, dun, dun. What you typing?
What am I doing? What?
Yeah. It's like, what are you typing? Or who's that typing?
That was me typing, so I muted myself. I'm coding, bro.
Oh, we'll keep coding then. Anybody remember what the natural log of E is?
I'm gonna guess 1.
Yeah. There it is. Yeehaw. Any questions on that one?
How did the 2 become negative the 2 tangent?
Because so when you do the chain rule derivative for natural log cosine, what is the derivative of cosine?
Negative sign.
Negative sign. So that negative came there, right?
Yeah.
And then the 2 times the negative sine over cosine becomes negative 2 sine over cosine, or negative tangent, 2 tangent x. What else? What else? Aren't these fun?
No,
You rather go the long way?
no,
You
I don't
rather
want any of it.
not do it? Yes.
Mhm.
Mm. I smell spaghetti. I mean, just imagine without logs going a long way. That'd be not fun. Sine over, yeah, that would cancel. Or maybe, that'd be weird. Okay, everybody good then? One thing.
Actually, I have a question, but it's not on the notes. It's on 2.6. Actually, I have 2 questions.
Well, we're still doing the notes.
Oh, whoops. I'll probably ask it afterwards.
Yeah, we have time after.
Perfect.
All right. Well, that means everybody's good with this one then. All right. All right. So that was the derivatives for logs. Oh, we had one more. Okay, sure. I'll knock this out. Okay. So 8 square root of x to the x. So we'll use logarithmic differentiation again. But before I do so, let's go ahead and rewrite this as x to the 1/2 raised to the x. And then this would become x to the x over 2. Because remember, exponent raised to an exponent, the operation is multiplication. So 1/2 times x is x over 2. Okay, so we'll apply the natural log on both sides. Natural log of y equals the natural log of x to the x over 2. And for the right side, that x over 2 just comes down and you get x over 2 times the natural log of x. Okay. So the right side is simplified, and then you will apply the derivative to both sides. And the left side becomes y prime over y. The right side has to use what rule?
Product rule.
Product rule. F is x over 2. G is the natural log of x. F prime is going to be 1/2. G prime is going to be 1 over x. Okay. So then we do f prime g, which gives me 1/2 times the natural log of x plus g prime f, which is 1 over x times x over 2. Okay. And then I'll multiply that y to the right side and fancy bracket 1/2 natural log x plus, and then what's going to happen to our x's on these two terms?
They're gonna cancel.
Cancel. So you'll get plus 1/2. And we're basically done. Y was the square root of x to the x. So you get y prime equals the square root of x raised to the x times 1/2 natural log x plus 1/2. If you really wanted to, or it makes you do it, you can factor out a 1/2 and be left with natural log x plus 1. There we go.
Why can you pull the, or 1/2 all the way out to the front?
Because everything's connected by multiplication.
Oh yeah, true.
Because you could have, I mean, you could pull it out and the 1/2 would have been here, but since it's by multiplication, you can just move it to the front.
Oh yeah, it'd be the same thing. I was just
Yeah.
confused. It wasn't a 1/2.
Good. All right. Everybody good with this one?
I am, but I have a quick question, and it
What's
has to do with the notes.
Yeah.
How does, I guess I'm really confused. How does the d over dx of the natural log of y equal y prime over y? Did I miss something?
Maybe I may have said it too fast. It's an implicit.
Okay.
It's an implicit chain rule, right? So remember that from the rule, if you have d over dx of the natural log of some function, let's say g, that derivative is g prime over g, right?
Oh, okay. I just didn't connect the dots. Thank you.
Yeah.
That
So that
makes sense.
means d over dx of the natural log of y, well, it would be implicit for the inside derivative, right? So the derivative of y with respect to x is y prime, and you put it over the inside, which is y.
Okay. Thank you.
Yeah.
Man, I don't even read the book anymore.
The book does the difficult notation. Makes it look all crazy. Yeah. All right, so now that finishes derivatives of logs, which means now we have the derivative of exponential functions. So the derivative of the exponential function a to the x, where the base of a is greater than 0, is going to be given by the derivative as a to the x times the natural log of a. So the derivative of a to the x is a to the x times the natural log of that base a. Okay. And then the chain rule derivative for that is going to be the derivative a to the gx is going to be a to the gx times the natural log of the base a times the derivative of that exponent. Oh, there's no other pretty way to write that. And now you have the derivative of e to the x. This one's great. The derivative of e to the x is e to the x. Marvelous, right? The derivative is itself. And then the chain rule derivative for e to any other function, so e to the gx, is going to be e to the gx times the derivative of that exponent, g prime of x. Okay. Those are your derivative formulas for exponential functions. So let's go ahead and try them out. Okay. So number 9, you have d over dx of 10 to the x squared. This is going to use the chain rule derivative for regular exponential functions. So is going to be, so the derivative is going to be the same function times the natural log of the base times the derivative of the exponent. So if we follow that formula exactly, what am I going to write?
Ten x squared times the natural log of a times.
Oh, not a, it's going to be the base.
I'm sorry, 10. I'm
There you
sorry.
go. You good.
10 times 2x.
That's it. So it's the same function times the natural log of that function's base times the derivative of the exponent of the exponent. And like I said, there's nothing else you can do here. There's no way to make this look pretty. So that's it.
So that's just the answer.
That's the ugly answer.
Okay. It's pretty if you don't have to do any more work.
I guess so. All right. Then 10. Y equals 5 to the negative 1x. Okay. So let's go ahead. This is going to use the same formula above, but let's go ahead and rewrite this one as 5 to the negative x to the negative 1. We're going to save ourselves some time because if you leave it like this, you're going to have to quotient rule the derivative of the exponent. So we can just flip this x to the numerator and make it negative x to the negative 1. Okay. And again, we're using that same chain rule derivative above. So if I say y prime, what are you going to give me?
Five of negative x with negative 1
Mm-hmm.
times the natural log of 5
Mm-hmm.
times negative, or would it be a positive x?
Mm-hmm. Be positive x to the negative.
2.
There you go. Brutal, right? Now you could make this one a little prettier if you wanted. Since they're all connected by multiplication, we could rewrite this one as 5 to the negative x to the negative 1 times the natural log of 5 all over x squared. Good stuff. Okay. And all we're doing is following those derivative formulas above. Just looks a little crazy. Okay. All right. 11. Here we're going to use the chain rule derivative for e to the x. So I'll write it out over here. You did d over dx of e to some function g. I'll say g of x. Then your derivative is e to the g of x times g prime of x. Okay. So this means that for this one, if I said y prime the derivative for e to the tangent of x, what are you going to write?
E to the tangent of x times cosecant squared x, or secant squared, sorry.
Secant squared x. That's it. Nothing else you can do. Sometimes it's just that ugly, right? Okay. 12. E to the negative 4x times the sine of 5x. So what rule are we going to have to use here?
Product rule.
Product rule. So f is going to be e to the negative 4x. And g will be sine of 5x. A bunch of chain rules here. Okay. So e to the negative 4x, that's going to use the chain rule derivative for e to the x. So if I say f prime, what is the chain rule derivative for e to the negative 4x?
E to the negative 4x times negative 4.
That's it. Or negative 4 e to the negative 4x. All right. And now, what is the chain rule derivative for sine of 5x?
Cosine 5x times 5.
That's it. Or clean it up to be 5 cosine 5x. And let's go ahead and follow our product rule. So we're doing y prime. So f prime g gives me negative 4 e to the negative 4x sine 5x. Let me move that down more. Okay. And then plus g prime f, which is going to be 5 cosine 5x times e to the negative 4x. Okay. We could say that's done. Or what could you factor out?
E to the negative 4x.
Yep. E to the negative 4x, and that'll leave me with negative 4 sine 5x plus 5 cosine 5x, and done. Any questions on that one? So now we have a lot more formulas to work with, right? Logarithmic and exponential. Okay. Hey, that was it. Okay. So we are done with these notes. If you got questions, then stick around and ask them.